Okay, so ladies and gentlemen, now moving on to the next topic. As all of you guys saw, we have on quantum security in reality. Use cases, solutioning, capabilities, arrangements, deployment, and benefits of case studies. The speakers for today on this topic, we have Dr. Debapriya Basu Roy, Assistant Professor from IIT Kanpur. We have Mr. Sunil Gupta, the co-founder and CEO, QuNu Labs Private Limited, and Mr. Kanak Kawadiwale, founder and CEO, Arishti Cybertech. Over to you guys.
You're on mute. Yeah.
Thanks, Chris. Sorry.
Yeah.
So, for inviting me in this beautiful session on the quantum security. So, basically, I will start as an accommodation. I'm going to start a few case studies on the post-quantum secure algorithms that I have done during my masters and during my career as a researcher. So, I will start, and then maybe we will go with to Sunil and then to Kanak. Yeah. So, I will start sharing my screen. Is my screen visible?
Yeah, we can see it.
Right. Okay. Am I audible? And you can see my screen, right?
Yeah, doctor, please go ahead.
Yeah. Yeah. So basically, I am a hardware security engineer, and my job as a hardware security engineer is to make sure that the communication between Alice and Bob are protected against attacks like side channel attacks, hardware trojans, and of course the fault attacks. Now, apart from this part, due to the recent advancement of this quantum computing, we are also now focusing on development of post-quantum secure cryptographic algorithms. Now, these post-quantum secure cryptographic algorithms are basically classical cryptographic algorithms, but they are secure against the quantum computers. So it is different from quantum key distribution protocols, which are basically based on the quantum phenomenon. Here, these algorithms are based on classical mathematical hard problems, but they can prevent the quantum computing threat, and that's why we are going to focus on this algorithm. So it will be background on what is quantum computing threat to modern cryptography. So this RSA and elective curve, they are basically the traditional public key algorithm solution that we generally use, and they are provide security against the classical computings, right? So as you can see in the RSA 1024 and ECC 25256, we have the 80-bit and 128-bit of security level on a conventional computer. However, in a quantum computer, this security becomes in polynomial time, and we can easily retrieve the secret key which are used in this public key algorithm. Therefore, you can see that if I develop a crypto system that is built on this discrete log or the integer factorization, which are the building block of RSA relative curve, then all the security protocols and all the products that are depending upon these crypto systems are going to be vulnerable against a quantum adversary. And that is the reason that there is a need to switch to other public key algorithms that are secured against this quantum computing threat. So NIST in 2017 started this contest where they are basically focusing on choosing the next generation post-quantum secure public key algorithm. So in round 1, round 2, round 3, we have consequently have 69, 26, and 15 submissions. And currently in round 4, we have the standards as key encapsulation mechanism of Crystal Skyber. It is lattice-based cryptography. Apart from the Crystal Skyber, we also considering other candidates like BIKE, Classic Matrix, and HQC. Now, BIKE, Classic Matrix, and HQC, they are based on port-based cryptography, and SIKE is based on isogeny-based cryptography. The algorithms for digital signature, Crystal Dilithium, again based on lattice. Falcon is also based on lattice, and Sphinx based on hash-based cryptography. So already people are basically switching to these algorithms and creating like OpenSSL, modified OpenSSL protocols, which are using these post-quantum secure algorithms rather than vulnerable elective curve or RSA algorithms. So I want to talk a little bit about this site or this associative cryptography. Note that site algorithm has recently broken 1 month back by a classical computer. So this algorithm that I'm going to talk about is not going to be considered for further consideration as it is already broken. But as my focus is going to be for this talk is on the hardware design and on the hardware implementations. So I think there is some very nice case studies or sorry, some very nice observations that we can do when we're talking about implementing these complicated algorithms like PSI or even lattice-based cryptography on hardware. So we all know that in a elliptic curve, the elements are point P on a curve group, and we share a secret scalar. Hello, sorry. Yeah. So we have a secret scalar k, and the corresponding isogen is as phi and kernel theta. So here the hard problem for elliptic curve diffie element is that given a point P and point Kp, we cannot find the point K. Similarly, in isogenous crypto system, it was assumed that given a curve E and the image of the curve E, we cannot find the mapping function or this image function. So it was built on some certain parameters. I'm not going to details of that, but to be very specific, we have some elliptic curve defined over some finite field, and we have some public points, and we are trying to create a map from the starting curve to an unknown curve, and that I'm going to use as my shared secret. Okay, and the hard problem in this case is to find out from the source and image curve the corresponding isogeny mapping. So the initial version of SITH has something, or this supersignal isogeny-based diffie element key exchange is something looks something like this. So we have this computation point RA, representing SA into PA plus QA against scalar multiplication, and then we are creating the isogenous curve EA from E0 using RA and EB from E0 using RB, and we are at the end of the day, at the end of this computation, we end up with some J invariant of curve which are going to be equal, and will be going to be used as a shared secret. Quickly, let's take a look at this hardware part. So in the hardware part, rather than going to the standard traditional number system, we are going to do something called non-linear number system. A non-linear number system, what we do is that when we are adding numbers, we do not do any carry propagation to adjacent words. Okay, so we do not have any carry propagation between the blocks, and therefore whether you are adding a 2-bit number or 4-bit number or 1000-bit number, your carry propagation delay is going to be fixed and your speed is going to be maintained. A basic example could be the carry safe form, when we basically put this r equal to 1 and n equal to 1, and that gives us a composite circuit of the carry safe form. Now, using this linear number system, you can build up efficient architectures for this finite field operations on this for this site. And at the end of the day, we build up something like this. So it is a complete coprocessor which works for all the psych operations like field multiplications, field addition, field subtraction. They're controlled by the AXI bus, which is communicating to an ARM processor. So basically, here we have the ARM processor. This is my AXI intercurrent, and this is my corresponding processor that we have built for the site algorithm. And consequently, we have found out that if we use our design, our speed up is going to be much faster compared to software implementation. Now, you can also integrate certain structure with RISC-V. RISC-V is open instruction set architecture is very popular now. It allows you to modify your own instruction. You can add your new instructions, which you cannot do in a standard ARM or Intel ISA. So RISC-V therefore is very attractive for someone like us who are researching actively on this domain. And for RISC-V, we can actually directly integrate these accelerators into this register bank of this processor, and you can again get corresponding overhead of the design. And this work, we have shown that compared to this standalone software design, which is running on Cortex M4 or Cortex A72, we are running much faster. Our clock cycle requirement is much significantly lower than what the standard software implementation requires. But we can go even further. We can actually keep on improving the performance, and then here I'm not going to details. Here we are actually optimizing the field applications, but at the end of the day, we will end up with certain architecture like this. which has their own instruction memory and own data memory. It is a complete coprocessor which you can program through this instruction data bus. And once instructions are loaded, you can execute the complete SIG architecture without requiring any software intervention. So that was a part for the SIG architecture design. Also, another important part for any hardware design is a side channel attack. The side channel attack, what we do is that we obtain the physical information like power and time, and from that we try to get the secret key of the implementation. A popular way to validate whether the design is leaking or not is to do a test vector leakage assessment analysis, which goes beyond this red line, that is 4 plus 1 is 4.5, which the system is not secure. And as you can see, the unoptimized site or unprotected site is basically going to be vulnerable against side channel attack. Another important parameter, another important class of algorithms for post-quantum secure public key is lattice-based cryptography. Now, in the NIST submission portal, we have multiple different lattice-based cryptographic algorithms. So this New Hope, Kyber, Dilithium, they are all the new different lattice-based crypto algorithms, and they are either based on this entity or some of them are not based on entity. So as you can see that all these algorithms have different parameters, and that's why it is very difficult for you to design a single architecture that can support all these algorithms. But using something called entity-friendly prime and something called entity prime lift, we can take this operation from this Q to Q dash, and then we can create a single multiplier operating in the domain of Q dash to do my complete entity operation. So we have chosen this particular Q dash, which can support all the lattice-based cryptographic algorithm, and this is the complete architecture for the entity, the modular arithmetic unit, and the coefficient multiplier, which switches between Montgomery multiplication and the standard multiplication using Solinus prime. So that brings us to the end of my presentation. I have tried to keep it really short so that we can have more time for interaction. So round 4 result for this post-quantum algorithm has brought up more design challenges, and as we have already seen, the SIG is broken, and it may happen the other algorithms that are chosen in round 4 will get broken in future, and that is the reason that it will be very foolish for us to rely on one particular algorithm. And for the upcoming period, we need to develop solutions which can support multiple post-quantum secure algorithms, such that if one of them get broken, we can at least switch to the other one. If we rely only on one algorithm, any vulnerability on that algorithm is going to collapse the entire infrastructure. And of course, we cannot forget the scenario of side channel and fault attack security, because they are a major concern when we talk about implementation. Thank you for your attention. So maybe
You want me to go next?
yeah, I am done. So Sunil, you can start.
Okay, thank you. Can you see my slides?
Yes, we can see your screen.
Okay, good afternoon, everyone. I'm from QuNu Labs. So what I'm going to be talking about, a brief on the company, if people are not aware of QuNu Labs. We are a startup founded in 2016 in IIT Madras Research Park, and we are the India's first and only company with a commercially ready and deployed quantum security product, both in the quantum physics as well as post quantum crypto algorithm. And what we have done is actually we have built an ecosystem of academia, public sector, industry, and we have also created uh, because all these products are manufactured, designed in India. So we have also created an ecosystem which has manufacturing partner, testing and certification partners. So the problem is, if you know, encryption, AES encryption is pretty good, right? And it's not possible to use a brute force on AES, and that's the reason if you see that nobody has ever broken used a brute force to break encryption. But what people hackers have been able to achieve is that they actually try to hack encryption keys, because in the last one decade, if you see last decade, most of the hacks that have happened on encryption keys have happened largely because of weak randomness, hard keys that are hard random numbers that are uses, repeated random numbers that are used, hard keys that are uses, and then of course the backdoors. So what we try to address problem is about how do we, if we are able to bring a quantum tech into key generation, right? Which basically means that we are able to generate a perfect random keys. And if we can distribute those keys using quantum key distribution over longer distances, and then we can store those keys and retrieve those keys securely and manage those keys in terms of key vault and key management, then we are pretty much addressing the vulnerable layer that exists in the crypto infrastructure today. So that is what QuNu Lab went ahead. And what we did in the last 5 years is we built a portfolio of products and solutions. First one, as I mentioned, we call it a holy grail. The root of trust is Tropos, which is our quantum random number generator, where we use a single photon's time of arrival mechanism to achieve a high throughput, high entropy random numbers, which uses optical source. These are one of the best in class. If you look at the random numbers, TRNG, uh, optical based QRNG are some of the best in class in terms of their high entropy. Then we have gone ahead and built quantum key distribution product, which provides a different configuration that I'm going to talk about a little later. But idea is that instead of using public-private key at Dr. Basu talked about it, we can't depend on those anymore. So that's one of the option is for us to go and symmetric keys. But then symmetric keys have a challenge of distribution, right? Because you have to encrypt at one end and decrypt the data at the other end. And how do you transfer a symmetric key without that getting exposed or hacked? So the quantum key distribution is the only technology that distributes, or basically it doesn't distribute, it actually generates a pair of key at the two ends, and is the only, other than one-time pad, is the only other information theoretically secure crypto that is available in the world. So we went ahead and built that available there today, and the customers are using it. And then, as you know, that QKD is largely dependent on private point-to-point networks, and it requires a dark fiber, at least one dark fiber. So it is not possible in the internet, intranet, and a lot of other public networks. That is where hard problem-based, mathematics-based, uh, post-quantum crypto algorithms and solutions come into the picture. So we have built a platform around that where, as Dr. Basu said, these algorithms are quantum resistant. They are not yet proven, uh, uh, as Psych was recently broken. So the whole architecture has to be in a way that it should be crypto agile. It should be possible for us to replace these algorithms in the future as new and new algorithms will come up. Also, standardization is about a year or 2 years away, right? We are hoping that this whole the final algorithm that are selected, they will undergo still a change. So that platform is available, and then of course quantum key management system, which is our Tholos, where we have the ability to provide keys or store and retrieve the keys, as well as encryption, right? If it's encryption as a service. So this is just to give you an idea, because people talk about it in theory and hardware wise, you should know to realize how it is. So what I'm showing you, these two boxes here, these are actual QuNu boxes shipped, manufactured in India, shipped to Europe. It is being used by a customer in Europe in a rack for in a quantum blockchain, right? In Europe. And now, just to give you up some of the configuration, and then there are use cases for that, is about you use Alice and Bob. We can connect to them over a optical network, optical fiber, 150 kilometer. And these are existing fiber. You don't have to lay a new fiber. It's existing single mode fibers that you can do. QuNu Lab has achieved 150 kilometer point to point that you can do. And then we have also available a trusted relay node where you can actually add uh, a pair of box, Bob and Alice, is a daisy chain, where you can connect multiple of them in a sequence, and then you can extend distance to 500, 700, and a kilo, any distance that you want. And so Indian Army is piloted this and trying to deploy this. And then the third one is where you want to do a different hub and spoke configuration, where, for example, there could be a one head office, bank headquarter, and then connected to multiple branches. It could be one headquarter of an enterprise connecting to different offices. So this is a hub and spoke where one Bob can be connected up to 5 LSS. Now, having said that, as I said, QKD, the quantum physics-based tech, has its own limitation. So in order for it to be deployed in the enterprise sector, where we are either the shared networks or private or public networks, we can't just use hardware-based and optical fiber-based solutions. So we have to use algorithmic-based, mathematic-based algorithms that we post-quantum cryptography, and we believe that security is always about a cost versus security that you want, right? So there's always a trade-off, and then in order to do that, you need to have a flexibility in your solutions, and that is where we have taken a hybrid path forward for our customers, where we have QKD solutions as well as post-quantum cryptography based solutions. And then we use hybrid based on, because hybrid gives you the best ROI, and based on the requirement, either you do QKD or PQC, or we also have implemented both together, right? For example, while QKD is the best in class in terms of computational security, right? Post quantum cryptography is resistant, is weak, and is already proven that is broken. But hybrid, if you do, then you get the best of the security. Similarly, in terms of ease of implementation, PQC scores over QKD. Long-term security, they're okay if PQC algorithms are good. Then both QKD and PQC provide you a long-term security against quantum computers. Intrusion detection is possible in QKD because of the optical fiber, the quantum properties of the photon that you can exploit, and then of course setting up the and network establishment. So what the way we have looked at it, if you look at it, uh, you look at three-step process, right? First step is root of trust, right? We don't want to use pseudo random numbers anymore. They're not good. They actually bring backdoors. They also bring weaknesses. So we recommend to uh, enterprises to first step process is go and use hardware-based quantum random number generator. You can have them in the data center, or you can actually use them as entropy as a service also on the cloud, right? So what you get is a random keys, good quality keys, high entropy. You can generate certificates, digital certificates using that, also tokens. Second thing, after you got a root of trust in place, then what you need is either you want to secure infrastructure or the stored data, or you want to do a communication link trust. So communication link, when you do, you can do quantum safe VPN based on quantum random number generator and both PQC algorithms. You can generate VPN tunnels for secure communication, for remote workplace, from client to site, or from client to client VPNs that you can do. You can do a quantum secure point-to-point messaging platforms or messaging applications. Like you can do a quantum secure end-to-end messaging applications. And then there are the using PQC algorithms and QRNG, you can build uh, uh, a post-quantum secure plugins, right? Email plugins, so that a specific emails, if you want that on higher security, you can encrypt those emails using this quantum secure plugins. So these are on some of the use cases here. I'm going to talk about some of them with pictures a little later. And then when you want to do a stored data trust, you can encrypt the data using quantum keys, quantum secure keys on the AES or on the other algorithms that you have. And then key vaults, right? You want to make sure that you are, and especially in a Web 3.2 world, where we are seeing that the trust is distributed, right? It's not centralized. And then in that scenario, you want to make sure that every node keys, the random keys, secure keys are securely stored in a key vault, right? So what we are seeing is that these some of these solutions actually offers you a very different paradigm security, which was not available earlier, where you can have absolutely random perfect keys. You can distribute them very securely over the distance, and then you can very securely secure the keys retrieve those keys or encrypt your data, right? So this capability, it was not available. This is going highly valuable in the post quantum world that we are living in today. So I'm going to talk about some of the use cases that take cryptography to mainstream, right? Uh, so if you look at it today, world is all in cloud. Either the cloud user, he wants security of its workload, the data in the cloud, or we say cloud providers who look to want security of the cloud, right? So the way we have look at it, you can actually the client would want, hey, give me a vault where I can keep my keys securely, or they would want, hey, I should be able to do a secure collaboration, whether it's an email or a messaging requirement. And then in order to do, and then you also want to do cloud resource management access when you want to do between the different clouds that you want to access. Then you want to do a, if you're interacting with two different clouds, then you want to make sure that uh, that you are able to create a secure tunnels. Similarly, application level, you want to do a quantum certificates, and you can also want to use entropy as a service to make sure that your keys are digital certificates are robust. So, and similarly, when you're doing a cloud provider, as a thing, he would want again to use QKD if he wants to make sure for the data centers or between the data centers that it's a secure communication and so on. So if you look at point-to-point networks, this is the way it happens today. Your data gets and goes to encrypted router, and then you have public network where you use public private key, and then you and AES encryption, and you encrypt the data. But what happens when you do one of quantum secure keys? That is where this protocol, that's a secure key interface protocol, which is the HC protocol now. The request goes from this router to QKD, and QKD generates a secure keys, and then give these keys to the encryptor, and he uses these keys to encrypt the data. And then other end, using the key ID, you take out the corresponding symmetry key, and then you decrypt the data, right? It's a very simple point-to-point use case that you can do. Now, there's another requirement. Wi-Fi is very used widely because of the advantage of mobility. But the challenge is you want mobility when you want mobility with highest level of security. That is not achievable today, right? So that's the reason people live in a very uncertain world where they trade off mobility sometime in the favor of mobility, but against security. But but today we're using a quantum tech and the post quantum tech, you can actually build a mobility on the go, right? And that is what we have done for our clients, where you actually on a Wi-Fi we create a quantum secure tunnels, right? And these tunnels allow you to choose the right algorithms on the both ends of the tunnel, PQC algorithms, and then provide a solution that gives you a complete end-to-end security, right? Other requirement is people want to put your workloads in the cloud. They want to use their content in the cloud. But now the problem is the keys. In that case, the keys get to the cloud service provider, right? So you don't want that, right? That's one of the biggest security risk you have. So QKD and PQC allows you to get a pair of keys, right? Same keys at two ends, which are there with you. And now it's like a bring your own key concept where you can like use the A and B of an enterprise. They can actually encrypt the content, put it in the container in the cloud, and which can be accessed by another user, which has the corresponding symmetric key, right? So now the security is in your hand, right? And at the same time you get the benefit of cloud, right? On-demand service that you want, but security remains in your tips, right, at your hand. So and then think of the other application. It could be like video conference application. Let's say is this thing, you have a prime minister office, he's talking to multiple ministries. Now today, if you look at Cisco terminals or Polycom terminals, this encrypted data goes out of these terminals on a public network. Now this network encrypted data can be harvested and can be broken later. So you don't want that, right? Because so that you can actually create again a VPN client and a VPN server infrastructure, right? Where you can again leverage QRNG and post-quantum crypto algorithms and make sure that all the data that leaves this terminal and arrive at the other terminal remains completely security at a higher level, right? So that even if this data is harvested, even tomorrow the quantum computers will not be able to break it, right? Then in the crypto world, now the people are talking about crypto trading platforms. Now this is a representative diagram that you see. You have a hot site, you have a cold site where you keep some of the crypto, and then you have another mirror cold site where you have a Q vault where you keep storage crypto. Now your idea is that, hey, when I'm using this crypto storage key vault, it should be secure. No should be. This is the one vulnerability nobody should be able to do. Then between the cold site when you're sending the keys or the crypto, then this should be secure. And then from hot site to cold site, and then from hot site to payment gateway. So now today what you see is that using both QKD. This is a perfect example of hybrid model that I was talking about. While we can use QKD based, because this is a very highly needs to be highly secure. So we use QKD, quantum physics based technology here. But on the other hand, we use quantum secure VPN, where we use PQC algorithms here and here, where probably we can afford a little lesser posture, but it has to be much higher than the classical security that we have today, right? So there's a lot of these solutions that are possible, are emerging now because of this reason, right? I'll stop here in interest of time, and happy to take questions later on. Over to you, Kanak.
Sure, Sunil. Thanks a lot. Thank you. I'm sharing my screen. If you can just confirm if it is visible there.
We can see the Kanak. Yeah.
Okay, great. Thanks a lot. So I'm Kanak. I'm the founder and CEO at Arishti Cybertech, and we're an IIT Bombay-based cybersecurity venture. I'm here to talk about the platform that we have built, which is more of enterprise messaging platform for sensitive communications using quantum technology. The product's name is Message Me, which we have developed as our product itself, a messaging platform. So before directly talking about the product itself, I would like to talk about why quantum technology and why choose quantum security over the traditional one. What are the particular problems that we relate to and we solve it at Arishti, right? So the first is the harvest now and decrypt later. I'll keep it very short and simple about the crisp problems that we are trying to solve over at Arishti. So first is of course harvest now and decrypt later. Sunil mentioned about it right now. So this is becoming a more of popular kind of an attack where in the latter future, when the quantum computers come in place, they'll be able to actually decrypt the data through their quantum computing or the vast majority of power, supreme power, and they'll be able to decrypt the encrypted data, which is again going through the open internet. Second is insecure communications, where sensitive communications are not so secured these days, and there is a lot of challenges in having a good communication. In this growing work from home era, I would say most of the communication channels or the business continuity depends on communication itself, and hence secure communication is something that is very important nowadays within the enterprises, in government organizations, in the private sector as well. And that is one where quantum security can play a major role, and I'll be talking more about that in the coming slides. At the end, weak cryptographic keys, as Sunil and Evan Doctor has already said about this. So using traditional cryptographic methods for generation of the cryptographic keys, cryptographic materials, session codes could be a vulnerable point in entire crypto systems. That's where these are particular things which we try to solve at Arishti using quantum security with the various methods. Again, on the notes of how long and how mature this commercial maturity of this quantum technology has been, when I talk about cloud based quantum technology, not just in the cybersecurity space but also in the machine learning, AI, deep learning. It has been used on a large scale, where Google has its own quantum computers or quantum capabilities known as CERC, which is again a Python-based quantum computing platform, open for researchers and for the institutes to simulate and to try to compute with their algorithms. Quantum TensorFlow is a cloud machine learning library being used on a large scale because there are a lot of pre-trained models in the deep learning machine learning models can be used and have got great results in that space as well. Microsoft has its own SDK known as Azure Quantum SDK. Again, open source but not so matured, but can be used particularly for simulating multiple algorithms, and can be openly used using Python and .NET language, particularly for researching purpose, I would say. And then comes IBM, which is much more matured kind of cloud-based quantum capabilities, which is known as Qiskit, a most popular version of cloud-based quantum computers, and can be used by researchers, by enterprises as well. The most matured, I would say, because being used by a lot of enterprises as well, and can be easily integrated within the enterprise solutions, within the enterprise architectures that are being currently used. So it also has a 16 qubit cloud computer, can be used by Python, simple and JavaScript based languages, and is currently being integrated within large enterprises as well. And lastly, Amazon, which has its own bracket named product. It has again three different subdomains: D-Wave, Rigetti, and IonQ. They have the access to 11 to 30 qubits of quantum computers, and again, these are mostly based on Python language. And these are the variants, particularly as per the need and as per requirements, because each and every in Amazon's cloud-based quantum computers, they have different variants of their quantum computing capabilities, can provide different use cases as well. Now I'll be talking more on the why go towards quantum cryptography, why go towards quantum capabilities. So if you see, most of the crypto systems today is being built on the base of random number generators. In that we have confidentiality, which talks about encryption and decryption; integrity, which talks about digital signatures; authentication, which talks about identity. And nowadays, if you see, there are a lot of startups and a lot of new innovations coming out there, which are talking about identity management, access management as well. And hence, in that case as well, in that use cases as well, random number plays a majority of role in that. And at the last, we use this in the day-to-day life as well: one-time session codes and OTPs. And these are being the most I would say, most of the use cases which has, or which creates a domination of a random number generator. And a lot of the crypto systems are built on the top of this random number generator itself. But being a developer, being a company, a lot of time will happen that we majorly focus on the open source kind of random number generators, which are again various types of random number generators. One is TRNG, which is based on, again, cosmological noise. PRNG is based on mathematical formulations, and hybrid could be a combination of hardware and software. But if you see, at the end of the day, this provide a probable randomness, and this causes an issue in vulnerability in the current existing systems, which we see that when we go ahead and when the quantum era comes in, this particular random number generators will be of a lot of vulnerable point of the point in the existing crypto systems. That's where QRNG comes in, because as we use quantum physics in this, as we are using complete non-mathematical based algorithms in this, and since we have a probable randomness rather than a probable randomness, that's what is very important nowadays. If you see in the current existing infrastructure or the current existing architectures of large enterprises, large products, they're currently based on PRNGs, TRNGs, or the hybrid kind of random number generators, but should always be focused on long retention of those keys, long retention of the codes, or long retention of the random numbers that are being generated. And hence, QRNG is a perfect solution where enterprise solutions should think of this, integrating this kind of random number generators, which actually means a lot when it is when we are talking about the more of crypto systems or cybersecurity products in enterprises. That's where we come on. We have built Message Me. It's a quantum secure messaging platform. It's not a messaging application, I would say. It's a complete end-to-end package with complete autonomy and with complete control over the data. We're built with a data loss prevention system in the place. So it's not, we don't call it as a messaging application. We call it as messaging platform with a lot of capabilities. It's a next generation enterprise messaging for critical communications using quantum technology. Why do we call it as a messaging platform? Is a lot of there are a lot of capabilities that we have built on the top of it, along with the quantum encryptions, of course. So we have built this system with the hybrid encryptions using quantum technology, which actually reduces the cyber attacks with the advanced quantum encryptions. Again, this is a hybrid encryptions, as also Sunil talked about it, that just using post quantum and it cannot provide a good kind of solution or ROIs. Particularly, hybrid encryption is a way towards it. So that's what we are using here. We are building this platform as a consent based critical messaging, and hence we at Arishti believe that consent is the future of security, and hence the data ownership or the data which is being shared within this platform, the ownership remains with the owner itself. Any data being shared within or outside the platform is completely depending on the consent of the owner. Third is admin controlled communication. So if you see with this platform, we have built this platform in such a way that executives can monitor, they can able to control, monitor, and also wipe out the communication sensitive data which is residing on the employee's device. So at the end, again, we have found a few use cases wherein the messaging forensics and audit in the banking sectors or in the financial sectors are of utmost importance. And depending on that, we have also built a forensic capabilities within this platform, where the enterprises can track about the file being shared within other enterprises with other peer members, and they can trace the actual journey of any data or any kind of sensitive files which are being shared over this platform. So if you see, at the end of the day, we have built a such kind of platform, first of its platform, not an application, which talks about complete messaging with the complete data loss prevention system, ultimate control, security, and monitoring capabilities within this platform. So how do we say that we have built this on the quantum technology, and what it takes to say that yeah, it's a quantum safe technology that we have built in this space? So, firstly, quantum technology based encryption. We use quantum technology. Again, we use cloud based quantum technology to integrate within the platform. Again, these conversations or the messaging that has happened or the sharing that happens on this platform are protected from the cyber attacks, unlike other platforms using cloud based quantum technology. We are using this quantum technology in order to integrate with the enterprises and lot of enterprises we have seen that data harvested, which is again encrypted data being harvested on their Secondly, it can provide the quantum safe encryptions, and thirdly, it can overcome the brute force attacks with as there's no mathematical formulation involved. Everything is completely provable randomness and not the probable randomness. On the top of it, if we talk about what is the framework that we use, this is completely zero trust architecture where the platform never trusts. It always verifies the access being given to the users, to the enterprises, to the executives particularly, and then talks about the consent based messaging. As I already discussed about this, how we are doing this, how this platform has being developed or being built for only enterprises particularly. So that's where we think that consent is the future of security, and hence once the security only starts from the consent itself. So as you move ahead, as we grow, this technology will keep on growing, but at the end of the day, there has to be a kind of synergy between security, between technology and a human interface, right? So that's where the consent comes in place. That's where we think at Arishti that consent can bring a lot of power to the user, to the owner of the data. And so the complete platform enabled with a DLP system, data loss prevention system, which can enable or help you share the data, communicate very well with your peers, at the same time maximizing your privacy and the security within the enterprises. So that's something that we have built for the enterprises now, and taking this ahead with the large enterprises, with the government organizations together. That's it from my side. Happy to have any questions regarding this. Thanks.
I think there is one question on the chat regarding how quantum key storage, distribution, and generation are linked to cloud, AWS, and Google Cloud, etc. So maybe Kanak, you want to answer this thing?
This is more of Sunil's question because they are providing something on the cloud-based key management solutions, and I hope that this question might be for Sunil, I guess.
Yeah. Okay. So any other questions?